Welcome to the webinar, The Great EV Debate. Will battery swapping replace fast charging? My name is Chloe Herrera, Senior Analyst here at Lux Research, and I'll be moderating today's session. Presenting today is my colleague Juan Camilo Cortez, Senior Research Associate here at Lux Research. Throughout the webinar, you can type any questions you have in the questions box on your screen, and time permitting, we will answer all the questions that we can. If your question does not get answered, please do not hesitate to email it to questions@luxresearchinc.com and we will respond. If at any point you experience technical difficulties, such as a frozen screen, simply refresh your browser and check that your internet connection is strong. Now, let's jump into the presentation.
Hi everyone, and thanks for joining. So today we will be sharing insights on how emerging charging technologies, particularly battery swapping, are reshaping the path toward large-scale electrification. As EV adoption accelerates, the charging experience has become one of the biggest bottlenecks to grow. Drivers want convenience, fleet operators need reliability, and utilities are trying to manage the increasing grid demand, all while automakers push for broader market adoption. Today, we will look at how these different stakeholders' priorities intersect and how technologies like fast charging and battery swapping fit into that ecosystem. By the end of the session, I expect that you understand the key advantages of battery swapping infrastructure, and based on that, you are able to form an opinion on what you think would be the future of electric vehicle charging. So in today's webinar, we will start by having a look at the EV adoption trends and understand the different charging technologies. Next, we will look at the EV charging value chain and highlight the main stakeholders and key priorities they have when they think about electric vehicle charging infrastructure. Afterwards, we're going to understand how battery swapping can simultaneously address concerns of multiple stakeholders, and we will do that by looking at our proprietary cost model that compares fast charging and battery swapping. And we will finish by looking at how those EV charging landscape would look. So first, I would like to start by looking at the EV adoption trend and available charging technologies. By 2030, according to the International Energy Agency stated policies and scenarios, electricity demand is going to more than double. One of the main drivers is the electrification of the transport sector. In fact, the electricity demand in the transport sector alone is going to more than triple by 2030. The figure on the right helps us identify the main subsectors in the transport sector that are driving this increase. Light and medium-duty electric vehicles will play the biggest role because of its higher adoption and will consume about 70% of the total demand. The remaining portion will be primarily used by e-bus and e-trucks, which despite lower adoption compared to light-duty vehicles, larger battery packs, and longer travel distances, make them take 30% of the total electricity demand. But considering that diverse charging methods create varied electricity demand and load profiles, utilities and grid operators will face new challenges in delivering continuous, reliable power and balancing the future power grid. So it is a fact that the electricity demand will grow because EV adoption is increasing. But we need to understand how charging technologies offer diverse charging power demands affecting the shape and magnitude of the power curve. So we will do that by looking at the 5 key EV charging technologies. First, we have slow chargers. They offer between about 22 kilowatts of charging power, and these are primarily found at residential locations. Next, we have fast chargers, which typically offer between 22 kilowatts and 3.7 megawatts of charging power. You will find this type of charging stations at highways, interconnecting corridors, and in large fleet depots. Next, we have dynamic and static wireless charging systems. So these offer between 22 and 150 kilowatts of charging power. 22 kilowatt charging systems could be used at homes and above 22 kilowatts in fleet depots or public charging sites. But today, there is little adoption of wireless charging systems. Finally, we have battery swapping, which typically relies on individual power modules to charge batteries. Depending on station open hours, turnaround times, and number of batteries, a higher or a lower power module capacity is required. Typically, each of these modules supplies between 22 to 150 kilowatts of charging power and can charge between 1 or more batteries. So we understood the technical side of the charging technologies, but identifying the priorities of key stakeholders developing controlling, or using EV charging infrastructure will help us to identify how swapping plays a key role in the future EV charging landscape. So let's start by looking at the four key stakeholders' priorities. First, we have drivers. For them, everything comes down to reliability and convenience. They want to avoid software glitches that make charging frustrating, minimize range anxiety, and extend battery life. At the same time, they are looking for faster, more efficient charging that fits seamlessly into their daily routines. Next, we have utilities. Their primary goal is to maintain grid reliability while keeping infrastructure upgrades to a minimum. As electric vehicle adoption grows, utilities are exploring ways to leverage behind-the-meter assets like stationary batteries or even EVs themselves to provide grid support and reduce grid strain. Next, we have automakers. For them, the focus is primarily commercial. They want to make EVs more profitable and increase adoption. Additionally, they are looking to expand into new markets and explore new monetization opportunities. Finally, we have charge point operators or CPOs. They are racing to stay relevant in a moving fast charging landscape. Their priorities are about reducing deployment timelines, minimizing site-level upgrades, and like automakers, explore new business models around energy services and user engagement. Now, let's look at how battery swapping helps to address the priorities of key stakeholders. To do that, we will look at qualitative and quantitative variables. In the quantitative part, we will look at the results of our proprietary cost model, which uses parameters like charging duration, nominal charging power, fleet size, daily travel distance, and vehicle and battery type to estimate the cost of swapping and fast charging projects. So let's start with range anxiety, one of the biggest psychological barriers to EV adoption that can also impact fleet operations. So if you look at the right-hand side figure, we can see that the charging time comparison between slow, fast charging, and battery swapping. Battery swapping helps to tackle range anxiety by directly bringing down charging times to under 5 minutes, essentially mimicking typical refueling experience. For drivers, shorter charging times mean less worry, better charging efficiency, and maximum vehicle uptime, which is especially critical for commercial fleets where every minute of the road affects operations. And for CPOs and automakers, the faster turnaround times means higher station utilization and a stronger customer engagement. Next, we have the simplified communication architecture that battery offers by minimizing communication protocols. So did you know that in public charging stations, about 45% of issues stem from software and vehicle-to-charger communication errors? Well, by minimizing the number of communication protocols between vehicles, charging stations, and payment platforms, software bugs are reduced, eliminating opportunities for errors or cybersecurity risks. This simplified setup increases system reliability, which is a key priority for drivers, CPOs, and automakers. And additionally, by minimizing cybersecurity risk, grid operators could face less communication or control challenges when leveraging such assets to provide grid stability service. Next, we have the improved grid management battery swapping offers by reducing peak power demand. To analyze the grid connection requirement, we use our model to calculate the number of chargers and power requirements for a 100 taxi fleet. We assume no dynamic load balancing algorithm is used and that charging optimization is based on vehicle daily travel distance. The figure on the right shows that charging power of a battery swapping system can be between 1.3 and 1.5 times lower when compared to slow and fast charging. This translates into lower on-site and grid infrastructure upgrades, therefore accelerating deployment timelines. In fact, a Chinese battery swapping developer deployed about 200 swapping stations across China in under 6 months. However, it is important to note that scaling swapping outside China is still a challenge. And in the meantime, CPOs and fleet operators will need to rely on commercial alternatives to scale charging infrastructure. Let's look at what Tesla is doing in the US. So the Oasis project is a California public charging station with 168 charging stalls, enough to serve a 100 plus electric vehicle fleet. This project is notable not only because it's one of the largest public charging stations worldwide, but also because it only needs a 1.5 megawatt grid connection. The reduced grid connection requirement is enabled thanks to the installation of an on-site 11 megawatt solar array and a 39 megawatt hour battery system. Altogether, it helped to bring the project into start operations in about 8 months. Using the solar and the battery system, Tesla Oasis is able to buffer the peak charging power demand and therefore minimize the grid connection. So Oasis demonstrates that by combining on-site distributed energy resources like solar and batteries, we can accelerate deployment timelines. However, it is limited to solar and land availability. And of course, it involves additional upfront costs to cover solar, battery systems, and the additional land that the solar array might require. Now, let's look at the more quantitative data and how the economics of battery swapping compare to fast charging in fleet applications. The results are obtained using our proprietary cost model that sizes and estimates the cost for fast charging and battery swapping stations. So let's start by looking at battery swapping in taxi applications. To estimate the annual equivalent cost of the charging project, we assume a 50,000 electric vehicle fleet, which is about half of the size of the New York taxi fleet. We analyze Europe, China, and the US, which have taxi fleets with varying daily travel distance, equipment, battery, electricity, and electric vehicle cost. We identified that in all regions, battery swapping project costs are about 5 to 9% lower compared to fast charging. This is primarily thanks to the reduced battery replacement needs and lower installation costs swapping offers. However, there are still challenges for commercialization of battery swapping outside China. One of them is pack standardization. But in addition to that, the lack of centralized depots of taxi fleets increases the complexity of optimally siting swapping stations for taxis. In contrast, in heavy-duty truck applications, we avoid that issue since the fleets are typically charged in a centralized depot. So this time, we run our model with a 20,000 heavy-duty truck fleet, which is about 1% of the total heavy-duty truck fleet in the US. We found that in addition to maximizing vehicle uptime to improve fleet operations, battery swapping is about 10% cheaper compared to fast charging infrastructure in Europe, despite the region has the highest prices for electricity, equipment, batteries, and electric vehicles. In China, we found that the lower electric vehicle and battery costs, two of the main variables affecting project costs, make swapping about 27% cheaper than fast charging. And in the US, similar to Europe, swapping saves about 10% in total project cost. A key point to note in this application is that vehicle upfront costs are about 10 times those of a taxi, limiting the transition toward electrified truck version, thus reducing upfront cost via novel business model like battery as a service, which can slash costs by about 50%, could help to speed up adoption. Additionally, an interesting point swapping offers for heavy-duty trucks is that if a modular swapping architecture is used, where instead of replacing the complete pack, you replace a smaller module, heavy-duty truck operators can optimize the number of required modules based on the travel distance to minimize battery weight while increasing vehicle payload. Still, there are challenges like requiring about 50% additional batteries to cover travel distance, and similar to taxis, further automaker adoption is needed. So to address this challenge, one of the largest battery OEMs in the space is partnering with multiple Chinese automakers to realize swapping in heavy-duty trucks. You might have already guessed, this player is CATL, Contemporary Amperes Technology Limited. The company has launched a standardized battery pack design for heavy-duty trucks, claiming compatibility with about 95% of trucks from 12 Chinese OEMs. At the moment, CATL has only deployed the solution in China thanks to supportive policy and funding, but the company aims to install 1,000 swapping stations to support heavy-duty truck electrification by the end of the year. The key point to note here is that since CATL holds about 45% of the domestic battery market, they are positioned to reshape the swapping landscape and promote battery standardization and adoption. So now that we have all of the pieces together, let's see how actually battery swapping compares with fast charging and battery integrated fast chargers. So battery swapping minimizes range anxiety. It can provide reliable charging by removing software communication bugs. It can minimize infrastructure upgrades on the grid and on-site by reducing the grid capacity connection required. It enables behind-the-meter energy optimization, allowing to maximize on-site renewable charging or enable backup power applications. It could unlock new revenue streams, enabling new monetization opportunities for CPOs and automakers by providing grid services. It can reduce upfront costs for end customers if a battery as a service business model is adopted, which can improve EV adoption. However, not everything can be positive. The main challenge is a key one that must be addressed is swapping is said to be commercial. That is, battery swapping is not interoperable with all vehicle types. So I would like to end the webinar with 3 main takeaways. First, battery swapping and fast charging are not mutually exclusive, and we will see at public charging sites both. But for fleets, battery swapping or often makes more sense due to vehicle uptime, and in addition, it offers lower cost of ownership and faster installation while still complementing wired charging options. Second, battery swapping can accelerate the electrification of medium-duty and heavy-duty vehicles. So for companies that are looking to adopt swapping solutions, the best path is to work with experienced players from China and perform pilots. And last but not least, battery swapping benefits the grid by integrating storage directly into stations. You can minimize peak power, and additional monetization opportunities can emerge by providing grid services. Thank you.
Thanks, Camilo. We will be taking questions now that you may have had during the presentation. And if you have further questions, you can type them in the questions box. If we do not get to your question on this call, someone from Lux will be in touch after the webinar. And it looks like we got a couple during the presentation. So the first one is, who are the key players offering battery swapping solutions outside of China?
Great, thanks for the question. So there are 5 or 4 actually key players that I would like to mention. The first one is NIO, which is targeting private electric vehicles. They have deployed swapping stations across China and also across Europe. Next, you have U-Power, which is a Chinese OEM that it's expanding to Southeast Asia and Europe through pilots with medium duty and taxi fleet applications. Next, we also have an American company, Ample. It's a US startup that have performed pilots in California with Uber and other ride-hailing fleets. And right now, they're expanding to Japan and performing pilots with taxi and medium-duty trucks. And finally, we have EcoSwift, which is a company from Singapore that has partnerships with a Chinese automaker, Sunny, and it's primarily looking at developing swapping solutions for heavy-duty trucks.
And then another question is, do you expect commercialization of battery swapping outside of China before 2030?
The short answer is no. I would not expect commercialization of battery swapping outside China before 2030. And the main reason behind that is that automakers, if they're willing to adopt battery swapping, they would need to change the whole vehicle design, because you need to consider that the battery pack could play a role as a safety component. Therefore, if you are willing to adopt battery swapping, you might need to redesign where the battery is placed, how the battery is placed, and you need to recertify your vehicle. And therefore, that takes time, takes a lot of effort, and it's something that at the moment, not all automakers could be willing to make. But in the near term, this could not happen, but in the long term, we might see more automakers getting interested into battery swapping, primarily because they could expand into new markets.
And it seems like this next question is a bit related in terms of, changing car design, but how does battery swapping affect vehicle to grid integration and adoption?
Yeah, so that's a very good question. And here we need to divide. So I think we should look at vehicle to grid integration for residential applications and vehicle to grid integration for fleet applications. So in residential applications, I don't think the battery swapping adoption is going to impact that much the adoption of vehicle to grid. But in fleet applications, I would expect that if battery swapping is adopted, we would not need a vehicle to grid at all in commercial fleet applications. The main reason behind that is that if you have a battery swapping module, or if you have a battery swapping station, you would likely prefer to just leave the battery there, take a new one, and start using the vehicle instead of leaving the electric vehicle park for providing vehicle to grid services and then recharge again. So the main difference is that with battery swapping, you can leave the battery, get a new one, and start using the vehicle again. While with vehicle to grid, you would need to leave your electric vehicle parked. And again, in fleet applications, that's something that not all fleet operators are willing to take, unless, of course, the monetization revenues that you can make are much higher than what you would make by leaving and having the vehicle on the road.
And then the other question is about the cost model that you introduced earlier. How do you change the different variables between regions? What goes into those different regions?
Sure. So what we did is that, of course, in each region, each vehicle type will travel a different travel distance. So daily travel distance is one of the main variables that it's modified between the three different regions. Of course, costs for the charging hardware equipment varies across regions, cheaper in China, more expensive in Europe and in the US. Of course, electric vehicle costs and battery pack costs are also there, part of the capex being cheaper in China, more expensive in other regions. And finally, of course, the operational cost, we only change the electricity prices that would change depending on the region. So to sum up, it would be the daily travel distance, capital cost, and the operational cost, specifically electricity prices.
And that looks like all the time that we have for questions today. Thank you, Camilo. That concludes our webinar for today. The slide presentation and recording from this webinar will be sent to all attendees via email. After leaving the webinar, you'll be prompted to complete a survey on today's presentation, and we would appreciate any feedback that you may have to help inform and improve our future webinars. Take a moment and check out our upcoming webinars on our website. Thanks for joining and have a great day.